Alright, so again, we see here I've got a GIF image borrowed from Wikipedia of this is what we call a four-stroke engine. This is a cross-section of a cylinder within a four-stroke engine. So your car, your automobile, as long as it runs on gasoline or compressed natural gas, operates in this cycle. Okay. Now, we use a four-stroke process because it's you get a more thorough combustion of the air-fuel mixture. You can get a little, in theory, maybe a little more energy out of it. There's one issue with it, though. It's only generating power 25% of the time right now, and it's done. And the rest of the time, unless it's in that power stroke, right, from 3 to 4, it's relying on other parts of the engine or the inertia of the rotation down here to keep the cycle going. Right? So in your car engine, you're going to have at least, most cars are going to have at least 4 cylinders, meaning you can stagger this process where each of these 4 cylinders is going through this process, but at any given moment, one of them is going through this power stroke. Right? And then now the next cylinder can go through the power stroke, and then the next cylinder can go through the power stroke. So at any given time, one cylinder should be driving if you have at least 4 cylinders. Right? Some your bigger performance cars, your trucks are going to have 6 or maybe even 8 cylinders, or some fancy cars will have 10 or 12. And you can stagger each of those cylinders to be generating power at different times. If it's a small lawnmower or a weed eater running a 4-stroke engine, and it's only 1 cylinder, those tend to we have to run those at a high RPM, rotation per minute, because again, you're relying, if you only have 1 cylinder or 2 cylinders, you're relying on the inertia of this rotation to continue the cycle. And so it can be done, but if you've ever driven a lawnmower, or if you've ever pushed a lawnmower with a single cylinder, most push mowers will have a single cylinder in them. If you ever pushed a lawnmower and you hit a rock and all of a sudden it stops, well, it's because that rock catches it, and it's going to force it to, you're going to catch it at one point in the cycle where it's not in the power stroke, and you're just going to stop the engine. And you have to unlodge the rock and restart the cycle. Okay, I'm talking a lot about, again, the Otto cycle is not the actual 4-stroke cycle. And if you want to look up, there's also a 2-stroke cycle. I'm not going to talk about that here. If you have to put, just a little bit here I could talk, if you have to put oil in your gasoline, it's running a 2-stroke cycle. But if the oil is in a separate compartment, that's a 4-stroke cycle. And if you want to learn more about that, there's going to be resources on the internet that will talk to you much more about that than I can. Okay. Let's talk about comparing an actual 4-stroke engine to the idealized Otto cycle that I'm going to test you guys on. Okay. This is the diagram, comparing a PV diagram of the two to each other. Right? So again, with a 4-stroke, you've got this other part down here where you're exhausting and intaking a brand new air-fuel mixture. Now, if you do this reversibly, there's no area. If it's done reversibly, there's no area in this lower portion down here. It's just a flat, thin line. That's the reason we don't include it here. We don't even have to worry about it here, because if it's done so reversibly, there's no area to this portion down here. Okay? So really all we have to worry about is this area up here, and notice how closely these two look. Right? This mimics that, and that's by design. Okay? So this is a lot easier to analyze mathematically. This is not impossible, but we're going to have to break it up into little chunks and be able to describe each one of these little areas mathematically and do integrals there. Here, this is pretty straightforward, and we've got the tools that we need already from chapters 5 and chapters 4 and chapter 7 to analyze this. Okay? And that's what we're going to look at in the next few coming videos. Okay? Again, the idealizations, because this is an ideal gas cycle, the idealizations we're going to employ for an Otto cycle to mimic a spark ignition sequence. We're going to assume that air is going to behave as an ideal gas. At high pressures, that's really a garbage assumption, but it's going to keep our analysis a lot more straightforward than using a more robust model that we talked about at the end of chapter 3. We'll just use ideal gas model. That'll be just fine. Again, we're going to assume that it's a closed loop. We're not going to worry about the exhaust and the bringing in of new air-fuel mixtures. We're going to assume that I've got a bubble of air trapped in a cylinder, that we're going to heat it up, and we're going to cool it back down. Okay? So it's going to be a closed loop, just a bubble of air, going to behave as an ideal gas. All of these processes are reversible. We're not generating any entropy. Again, it's an ideal cycle, so we're going to look at this is the best case version of an engine, and it gives us an ideal idea of what is the maximum performance we could expect from an engine that operates the same as this Otto cycle engine that we can compare it to. Okay. Again, not going to worry about the combustion process. Leave that upper level chemistry to those of you that go on to study this in some junior or senior level courses. You probably wouldn't have to have an entire course in organic chemistry, but you would need some basics there. Okay. So we're not going to worry about the combustion here. We're just going to say it's heat in, right, and then expand, and then reject heat, heat out, and then compress to repeat the cycle. And we saw that earlier. And you can see here, so we've seen this already, but this is just kind of a rehashing of it. Isentropic compression from 1 to 2, right? So compression, that's work in. So work in, from 1 to 2, work in. Constant volume heat addition, so that's heat in, heat from 2 to 3. Isentropic expansion, that is the work out. Whenever we expand, we're getting work out, so that's the work from 3 to 4. And then finally the constant volume heat rejection to get us back to state 1 from 4 to 1. That's a heat out term, so that's minus here. That's equal to the change in the internal energy of the gas, the air within the cylinder. And I think I've got, because it's a cycle, it returns back to its initial state. This is U1 minus U1, because it's a cycle. I'm going to write. There's only so much I'm going to try to write with my right hand. And there we go. Because it's a cycle, the internal energy goes back to its initial state. Okay? So the sum of all these will add up to be 0. Okay? So that's one equation we can use throughout for all of these example problems that we can look at. Okay, let's see if I got anything else after the example, because I don't want to. Oh no, this is so one more real important concept here. I told you, and because I wrote it down, I said this is really important. I'm going to write down the compression ratio. Why is this so important? Because the efficiency, the performance of an Otto cycle really is only a function of the gas you use, so the K value, the ratio of specific heats, C sub P over C sub V. So this is the K value. So the only thing that's going to determine the maximum efficiency for this cycle is going to be this K value, the specific heat ratio, which is a function of the gas, and the compression ratio. And notice what happens. As we increase the R value, right, I get a larger quantity here in this denominator. So as I get a larger quantity in this denominator, this negative quantity becomes smaller. So as R increases, this negative quantity becomes smaller, and we approach 100%. So the idea is the higher the compression ratio, the more efficient this engine can become. Now, the problem with that is you run into a problem with the substance we're burning. That's gasoline or octane. It is not stable. It is literally liquid explosive. And the problem is if you compress it too much, it will explode on its own. And whenever, if we go back and look at this, right? So if it explodes now, as that piston's continuing to try to drive up, and you got an explosion occurring as that piston's trying to compress, boom, it literally blows the engine up. That's not good. That's what we call throwing a rod. You literally blow up one of your cylinders. If you increase the compression ratio too much, because of the nature of the fuel source, that's actually bad. So if you buy a high performance engine, let's say you go buy a Corvette or like a Roush Mustang or some really, a Cobra Mustang, something like that, or a Lamborghini, you're not going to run cheap gasoline through those. You're going to have to go buy the expensive high grade stuff because that's a higher concentration of octane, meaning we know exactly when that's going to blow up. The higher the concentration of octane, the more likely we know exactly when that's going to blow up if you compress it, and it's not going to blow up too soon. So the high compression, high performance engines, you can run a higher compression ratio without the gasoline blowing up on its own, so long as you provided a good fuel source. If you buy the cheap gasoline, it's likely to blow up before the cylinder finishes compressing, and that's not good. Okay, so that's the reason in a high performance engine you have to run higher octane fuel. Okay. There is one additional term here. I'm not going to spend any time on this. If you have questions about mean effective pressure, let me know. It's a pretty simple formula to determine. You take the work out from the engine, and the mean effective pressure would be the displacement volume multiplied by the mean effective pressure. That gives you the net work out. I don't see this term being used outside of the textbook, so I really don't spend a lot of time talking about it. It's a simple formula. I only mention it because some of the problems that you see in Chapter 9 do ask you to compute it. I think I might have even assigned it. If the problem that's assigned asks you for the mean effective pressure, I'm not going to grade you on that part of the problem. I'll grade you on the rest of the problem. If you want to go through it, it's a simple calculation, but that's more class time than I really want to spend on it. It's just mentioned it's a thing. This textbook and some other textbooks like to talk about it. It doesn't really mean anything, but it's a thing. So, okay, and that brings us up to the examples. So we'll pick up. So I don't want to overload you with stuff after the exam going into the weekend. We will look at, on Tuesday, I'll publish videos where we look at this example problem, an Otto cycle example problem, and then we'll review for the final exam. And depending on how long those videos go, I might talk briefly about Diesel and Rankine cycles, but that's not necessarily required for this course, at least not most places. So that's plenty for a lecture after an exam. So I'm just going to stop us there. Send me an email if you got questions. Leave me a comment below. Find me in the chat room on Canvas. Tuesdays and Thursdays, noon to 1. I'll try to be available a little bit more tomorrow since it's exam day. If you've got a specific time, some of you guys have done this. If you've got a specific time you want to meet me in the chat room, or we want to try to do a Zoom call. Sometimes my bandwidth's not very good, but I'm happy to try it. We've done that with some of you guys, so send me an email and say, hey, can we do a Zoom call, or can I meet you in the chat room at this time? And that tends to work okay. I'm happy to do that. Just let me know. But I don't know if you don't ask. So, all right, guys, stay safe out there. Stay healthy. Wash your hands. Wear your mask. Stay social distancing. All that stuff. Let's get back to the classroom as soon as we can. But we gotta do the right things first. All right, guys, I'm done. Have a good rest of your week. Have a good weekend. Good luck on your test if you haven't already taken it. If you haven't already taken it, well, go take it. Let me know how I can help. Talk to you guys later.